Maybe. There we go. Hi, everybody. Welcome to today's Fiveable Q&A, open questions, all the wonderful stuff on AP Physics. My name is Peter Apps, and basically, if at any time you guys have questions, topics you want to go over or stuff like that, please just shoot me a message in the chat, and we will do our best to get to it. So let's kind of go over what I've got planned, and then this has changed a little bit because I've already got a couple topics to go over here. So just as a recap, in case you didn't know, Fiveable streams every day pretty much. Today's Wednesday, so it's Science Day. And we've got tonight Environmental Science Physics at 7, Bio at 8, Chem at 9. And again, also check out all the other many different streams going on. We're also going to continue this 1 o'clock to 2 o'clock time segment doing Q&A, probably up until the exams actually start. So speaking about the exams, more detail about what's coming up. Because of the changes in the exams, and in case you didn't know, AP, because of school closings and stuff like that, has decided to modify what's on our exams. We are just doing units 1 through 7. So that's kinematics or motion, forces, circular motion, gravity, energy, momentum, simple harmonic motion, and rotational. Electricity, electrostatic, sound, and waves are not included on this year's exam. So we're changing. Tonight's stream was supposed to be on electricity. We're changing gears a little bit and going to momentum again, just because that's a common choice for a lot of AP questions, especially for response ones. April 1st, we are doing our practice stream again, FRQs, Q&A, open to any topics you want to cover. That's at 1 o'clock next Wednesday. And then next Wednesday night, we'll do energy and momentum kind of combo FRQs. So a little bit of momentum in a question, and then you use the momentum to find energy or energy to find momentum, back and forth. All right. So, of course, please check out and follow at Think Fiveable on all the social media places so you guys can keep up to date with whatever we're doing as we try to figure out what we're doing with all these changes coming down from College Board and stuff like that. All right, so that's kind of the stream update, exam update. Let me see if I can pull up the actual AP thingy here. Hold on, let me change what I'm grabbing onto and find that tab so you can read it to you exactly, so I'm not going to forget. There it is right there. All right, so AP updates, because of all that's happening in the world around us, we are changing our stuff. AP is putting out some resources. So here's the big thing right here. Exam questions are going to be done at home, or maybe if your school is going to go with it, some centralized location, but they're all done online. It's a 45-minute free response exam at home. So no multiple choice, and 45 minutes of free response questions probably means we're looking at 3, maybe 4 free response questions, but it will really depend on if they're going to drastically change the style and stuff like that. We as instructors won't know until April 3rd what those details are actually going to look like. So right now we're as in the dark as you guys are, but we know it's free response based, no multiple choice, stuff like that. So for us, as I already mentioned, AP Physics 1, we are only covering units 1 through 7. 8, 9, and 10 are not included on there. And there is no clear date as to when we're actually going to take this exam. So for right now, it's online at some point in the future, and we'll get more details as we get more details. But that's where that's going in there. Hopefully next week, we'll get more details and be able to share with you guys, this is the date or dates, these are the plans, this is what to expect and stuff like that. So as always, keep your ears open. We'll do our best to keep you guys in the loop as we need to for that. All right, so back to this sort of stuff. There you go, present. and get big again. Okay. So there's exam updates. So we want to start off with Q&A on anything. And there were quite a few questions on there. Let's see what we got here. Rotational dynamics, torque, and lever arm. Yes. Okay. So I will add that in really quickly. So I've got 3 topics so far suggested. And if we need to do more, we will definitely do more on there. But the first question that came up was on Atwood machines. Okay. So Atwood machines are basically, we're looking at forces, right? We're looking at some object hanging down off typically a pulley and 2 objects hanging around them. And then one goes up, one goes down, something like that going on. Here's a sample problem that I just pulled out of my question bank here, dealing with Atwood machines. So let's go over this while we try to solve all the things about Atwood machines. So first off, Atwood machines and anything like this, if we look at the question, we've got a pulley. That pulley is considered to be frictionless and have very, very, very little mass, which is really useful. If that pulley had mass, we'd have to change this around a lot and do some torque questions in there as well. And I can talk about how we would do that once we're done solving this question. Well, excuse me. But for right now, we're going to assume that this is just a plain magic pulley that has no mass, no friction, no tension, nothing like that going on there. All right. We're asked to find some accelerations. Boy, I wish I could make this disappear. Some accelerations and some tensions. All right. So we're given a bunch of weights and we're looking for accelerations and tensions. This to me, and hopefully to you, says we're going to use Newton's laws. So our biggest, most popular sort of thing is, of course, Newton's second law. So I'm going to pull up my little webcam here to do a little recording, and we'll solve this problem. Let's see, is it going to work? Yeah, there we go. Okay. So we're told, let me sketch this out again so you guys can see we got a block, 1 block, 2 blocks, and then another one on this side. Okay, so that's kind of our setup here. We've got a 2 kilogram block, a 1 kilogram block, and a 4 kilogram block all sitting around there. Can you see that? Maybe we can move this way. That's better. Okay. And we're looking to find the acceleration of that guy. Well, a couple big important ideas to look at here first. Part number 1 is that all these blocks must have the same acceleration. They're all connected with the same string. They're all able to have the same exact acceleration. So while they say the acceleration for the 4 kilogram block, really this means the acceleration for all of the blocks because they're all connected with that same pulley or same string to each other. All right, now there's a couple different ways you can approach this question. And I'd love to hear you guys put up in the chat which way you want to do it. We can either do this block by block, or we can do the entire system together as one. I'm not sure which way your teachers taught it. So those are the 2 ways that I would present this to my students. So which way do you want to do it? Entire system? Both ways. Okay, both ways. Excellent choice. Okay, so since we're doing it both ways, let's do the big picture first. Okay, they're both going to start off with the same basic idea that, hey, all the forces added together equals MA. Ignore my really bad sigma. That just means adding all the forces together, in case you didn't know that. And we're going to look at the entire object. So everything in there is connected to each other with a string. That means there's only a couple forces that are actually important here. We have the weight of block 1 pulling down, M1G. We've got the weight of block 2, M2G. And we had the weight of block 4, I'll call it M4G, pulling downwards. Everything else in there, all the tensions, the tension going up, the tension down, up and down, are all internal forces. They are caused by something inside the system we just chose. Okay, and because we defined our system as being the blocks and the pulley, the only thing outside of that is gravity. So when we look at doing Newton's law for this, we can say, okay, well, these two forces must act together to pull the block that way. And M4G is trying to pull it the opposite way. They are opposed to each other, which means we need to make the call. One of these needs to be positive and one of them needs to be negative. Now, in my case, I know 4 is bigger than 2 plus 1. So I'm going to call this way positive and this way negative. So if we're rotating in a clockwise direction, that's a positive one. If we're going the opposite direction, that would be negative. So my Newton's law equation becomes M4G minus M2G minus M1G. So all the forces going on here, the weights of those blocks, M4 opposed by the weights of the other two blocks, must equal the mass. Now, because we're looking at the entire system with everything going on in here, we need to look at the entire mass of the system. So this is M1 plus M2 plus M4 all times A. Right? All the forces, and we get all the masses out. Okay. So all the forces means all the masses. And that's how we're doing this in general here. So now let's do a little simplifying. This is the algebra part, really. How we get there, that's kind of up to you guys. I like to have my kids factor out and then do stuff. So this is M4 minus M1 minus M2 all times G over M1 plus M2 plus M4, and that must equal A. And now we throw in some numbers. 4 minus 3, so that's 1 times G, so that's 10 over 1 plus 2 plus 4 over 7 must equal A. So our acceleration is 10 sevenths, or whatever that works out to be as a decimal. And if that's where calculators come in handy. And of course, mine is not around. So we'll consult the computer for a second here. 10 divided by 7 is about 1.43 meters per second squared for our acceleration. All right, so that is the first part. That is the whole system, the big picture idea. Questions? All right. Okay, so that was the whole system. We can also do this block by block. If we switch the signs, it should work. Yes. If you suddenly decided, oh, this was if that happened to be a negative and this happened to be a positive direction, yeah, minus, plus, plus, minus, plus, plus, you get a minus 10 sevenths, which again is talking you're going in that clockwise direction. So whichever way you choose to be, it'll work out to be the same thing as long as you're consistent with it. Most of the time, these questions here are going to ask for the magnitude of the acceleration or the absolute value of it. So the negative sign doesn't matter at all there. But this would be perfectly fine if you chose to make that negative and carried through instead of making it positive like I did. No difference at all in the work and no difference at all with gaining credit, losing credit, sort of stuff like that. All right. So now, this is by far my favorite way of doing it because that's simple and quick and most importantly, simpler on the math. The other way to do it is to do block by block. Now, this is going to have advantages later on, because I know the questions coming up, we're going to have to find tensions. And there were no tensions at all in this system setup. We got rid of them all in here. So doing it this way is more work to begin with, but we'll save time later on because of where this question is taking us. All right, so block by block. We're going to look at each block individually, look at the forces on it, and then make up 3 different Newton's law equations. One for block 1, one for block 2, and one for block 4. We're then going to use systems of equations to put them together and make the math all work out wonderfully, which hopefully is going to work out super well. All right, so I'm going to start with the block 1. This doesn't matter which one you choose. Okay, so block 1, I have, so sum of the forces, this is block number 1, equals m times a. The forces on block 1, there are 2 of them. There is tension going up and from the rope, and there is gravity pulling down. I know from looking at this picture that we need to go in a clockwise direction, which means we're going to call let's call it tension 1 minus m1g equals m1a. Okay. You can use a different symbol for tension. I'm going to use a capital T, and then T1 will be the tension between, let's see if I find a different color here. The tension, that's the same color. That's not going to work. My supply of pens is lacking right now. Hey, green. Green will be a good choice. So T1 is going up in that case. All right. We do the same thing for block 2. Sum of the forces on block 2 must equal MA. So block 2 also has, or block 2 has 3 forces acting on it. It's got tension pulling it down between these block 1 and block 2. It's got tension pulling it up between block 2 and block 4. And it's got its own weight pulling downwards. So this one's going to look like T2 minus M2G minus T1 equals M2A. Right, we're T2, again, so T1 is this up and down pair here. T2 is going to be up there and up on block 4. And then finally, we can continue on here with block 4. All the forces on block 4 equals MA. This is M4G minus T2 equals M4A. So we get our 3 different equations. And now all we really have to do is solve this one for T1, maybe solve this one for T2, plug them all in, and then we're pretty good. And if we do that, we get T1 equals M1G plus M1A. This is T2 equals M4G minus M4A. And we plug them in here. So M4G minus M4A minus M2G minus M1G plus M1A equals M2A. And this is the part why I don't like doing it this way, is this looks messy. That there's no nice way around it. This is the point where my kids, if they were going to make a mistake on this, would make the mistake in this plugging in and solving process. But we can combine some terms. Let's see here. Let's get the A's over the other side. So that's a negative. That's a negative. So M4G minus M2G minus M1G equals M4A plus M2A plus M1A. And then factor out M4 minus M2 minus M1, all times G, equals M4 plus M2 plus M1, all times A. Lo and behold, this line right here is exactly the same as what we started with way up at the whole system one. So we're going to get the same answer. It gives us the same results. We still get this A equals 1.43 meters per second squared answer. This way, we just go block by block and systems of equations. That's the way we have to do it. This is also, unfortunately, the way we have to do it. Is the system way better time-wise? Oh, yeah. Yeah, if this was a question on an AP exam, I would definitely do it system-wise. It's quicker. It's more straightforward. There's less math to screw up. Yeah, this way is what I teach my kids. This is their main method of going to it. If they forget or freak out, like, I don't know how to do this method, then we also teach them block by block so that they have that to fall back on. But looking at the system, if you can encompass all the objects in one nice big picture, it makes it a whole lot easier to do. Also, I mentioned at the beginning of this problem that this pulley has no mass, right? It's a magical massless pulley and stuff like that. If we get into the point where you see a question like this, where the pulley has mass, where the pulley is large enough that we have to deal with torques and angular accelerations and stuff like that, then you've got to do it block by block. Simply because we're going to have another object to put in here that's really difficult to do with a whole system sort of thing. So knowing how to do both is really useful. As far as AP exam questions go, the last time they did one like this, solving it with the whole system worked, and it was super clear and easy to do both parts, both the mathematical part, and they turned it into a what if. What if we add another block to it? What would that change? Whole system definitely worked better for that. All right. So there is a quick Atwood machine sort of idea here. Basically, we go through free body diagram as one of the parts. We label the system and draw it out. So if you had to do a free body diagram for this question, what they would probably give you is, I don't have a picture of it. They'd give you the diagram with the blocks, and then you just have to draw everyone on there. So drawing those in, because they're going to want individual forces on everything if they're going to make you draw them. And then when you do the math behind it, you can say in a sentence, or like I did here, hey, we're looking at the entire thing, which means I get to ignore all the tensions because they don't matter when we're looking at the big picture for this. But again, that's a massless pulley with nothing going on here. Massless, frictionless, stuff like that going on. Okay. Other questions on Atwood machines in general? Okay. All right, so let me close this out for a second here. The next topic that was requested, and again, if you guys have more topics you want to see, throw it up in the chat or use that Ask a Question button down there, and I will do my best to answer them. The next topic was going to be focused on, let's get rid of the laser pointer, conservative and non-conservative forces. So let's back up a second here and talk about the difference between those two kinds of forces. A conservative force is a force that how you get from point A to point B doesn't matter. So a great example of that is gravity. Gravity is a conservative force because if I take my marker and I move it from this point up to this point, there's a difference in height here, and I can figure out energy and stuff like that from it. It takes a certain force to go from there to there. Now, it doesn't matter if I go in a straight line or if I go way off to the side first, then around and around and around and around. It still gets from start to end, and that's what matters. Gravity is always conservative. Yeah, it doesn't matter how you get there. We care about start point and end point for those things. Okay, so something like gravity or a spring force, or another good example. Those two are the common ones. Gravity and springs are conservative. Friction, on the other hand, is non-conservative. Friction, because it depends on the distance you actually travel, the path you take. if I go straight up, I have a small difference, a small path with friction. But if I take and then I zoom back and forth, back and forth, back and forth, the distance I took was much larger, which means that the frictional force takes more energy away from it. Basically, if you're dealing with a non-conservative force, we care about how you get there. The path makes a difference. Whereas a conservative force like gravity or a spring doesn't matter how you get there. Tell me where you started, where you ended, and we'll be able to calculate it the same for every single path on there. In fact, let me do a little college textbook sort of idea here where we're going with this. So the big idea with this is that when we're talking about non-conservative forces, they basically will take away mechanical energy. So if we are looking at a situation where we have friction going on in a problem, we cannot guarantee that potential energy equals kinetic energy all throughout that system. What we can say is that total energy doesn't change as long as we're taking into account the fact that we are losing energy, mechanical energy, because of that. So common examples, again, if we're looking at our system as being this masses and springs sort of thing. So at the beginning, we have all potential energy due to gravity. At the lowest point, we have potential energy due to a spring or elastic potential energy. Those amounts are equal to each other. And then somewhere in between, we have both kinetic and potential going on. If we don't do that, if we look at the B example here, we have a non-conservative force. We have friction or heat or sound or other stuff like that going on. All the energy we start with falls down, and then it's gone. It's not potential anymore. It's not kinetic anymore. It's not in a spring anymore. It's not mechanical in any way, shape, or form. We have lost that energy now because of these non-conservative forces going on. Okay. Torque lever arm. So how do we account for them in the same formula? All right, so that's a great question. Basically, when we go through this, if we're doing a question on it, we're going to look kind of like, go back to my thing where I can scroll. We're going to kind of look at like this. So we know that in all cases, we can talk about work being a change in energy. So if we have work, we're going to change the energy of the object. The total work, the work we're going to see come out of it, is always the sum of all the conservative forces plus all the non-conservative forces. So if we have, for example, pushing a block up a crate, or pushing a crate up a ramp, we have this applied force. That's our force of our push. That's going to do work. We're going to push this up the ramp. We are doing work on this. Okay? That work is probably more work than the energy we're going to get out at the end, because we have all this work being done, and friction, our little lowercase f over here, is going to take away some energy from that. It's going to take away some of that potential energy we're gaining. It gives us negative work. So you can think about it. Our pushing on this block is doing positive work. The friction's doing negative work. So the total work going on must be what we're left with on here. So basically, we get to this equation down at the bottom here. And this is what I typically have my kids remember. It's work in, or energy in, energy out, and then the work done by friction or some non-conservative thing is going to remove energy or add it in. So I just have my kids add in this, plug the value from networking to double working. Yeah, if that's what the question's asking for. In this case, if it's asking for maybe potential energy or the difference between the work we did and the energy we got out at the end, then we're going to look for something slightly different. But yeah, basically, what an energy diagram, let me draw it out. So give me a second to switch back to the camera here. That's probably a better way of doing this anyway. Camera. This one. All right. So if we're looking at this, bigger. There we go. Okay. So if we're looking at this, we've got our box on our ramp going up. We're doing some force F here. We have some friction. I'm going to do FF on there, going back the other way. And we want to talk about energy going on. So let's assume, because the diagram I was using didn't really say, let's assume at the beginning, we're not moving. So no velocity going on there. And at the end, our final velocity is also 0. So we're going to start with this not being pushed or being pushed up the ramp, not moving. I'm going to end with it sitting on the ramp, also not moving on here. And we're going to say by the end of this, we go up a distance h, because that seems to be a reasonable idea. Okay, so at the start, we've got our little bar graph here. And I really need to move this so we can see better. Okay, different kinds of energy we can have. We can have potential due to gravity. We can have kinetic. We can have potential in the spring. And then we can have, I guess we'll leave it like that. So in the beginning here, we're going to say we have no energies here. I don't have any potential. I don't have any kinetic, and there's no springs going on here. Okay. At the end, what I would do is have those same ones. I suppose I should put in a work term over there too. In this case, at the end, I end up with some potential. I end up with no kinetic, no springs, and then I will have some negative work done by friction in this case. So that the total energy, actually, this should be something like this. So we would add some work in, and then why is the work negative there again? So this work is negative because friction opposed our direction. The way I teach my kids is they think about it, if we're adding energy into it, then it's positive work. So if we are increasing potential or increasing kinetic or stuff like that, that's positive work. If we are taking away energy, like in this case, that friction is going to take away some energy. It's going to turn it into heat or other stuff like that. That's why we're going to call this work negative, because it's taking away energy, not adding in more energy. All right, cool. Okay. Does that make sense? Okay, so yeah, basically for a diagram like this, and this is not exactly the way that it would look if I had a AP question, I could show it to you, but I don't right now. But basically the idea here is that you'll have some before and some after. There's positive work done by this force, so this is positive work. And then this one gives you negative work. And the difference between these two has to be your change in energy at the end. Initial energy plus net work equals final energy. Yeah, that's a good way to put it. I typically do initial energy equals final energy minus the work done by friction. But yeah, that works perfectly well. Energy at the beginning plus or minus any work we have going on, and then final energy is a good way to think about it. So to say something like, let's see, potential initial plus kinetic initial plus the work done by stuff equals the final plus the kinetic final would be a decent way to start with that sort of thing. Okay, that's done. And that's what I had at the beginning here. So let's see, what other topics do we have here? We got waves, simple harmonic motion, rotational dynamics, torque lever arm, oscillations, simple harmonic. Okay. Yeah, so there's a couple simple harmonic things. So let me go over that to start with here. So simple harmonic motion. Again, this is the last unit on this year's, no, sorry, that's unit 6. Our last unit's on rotational motion on there. But basically for simple harmonic motion, we're going to look at something saying like we've got a spring Well, let's make it go the other way. And a block attached on it with mass M. Right? This is put on some nice frictionless surface, and we're going to basically look at how this block moves over and over and over and over and over again. So a lot of this stuff is covered with energy. So you can think about it as we pull this block back to its maximum point, which we'll say is right here. This is where we have the most potential energy in a spring. And at its minimum point, we also have all the energy in a spring. And then at the middle, which we'll call the equilibrium position, we have the most kinetic energy going on. Typically, these simple harmonic motion questions don't deal with any non-conservative forces because the spring force is conservative. It just depends on where you are, not a not how you got there, just simply what's your X position, and then this is the thing going on. So a lot of these will do things like, okay, well, here's the kinetic energy as a function of distance. What's that graph look like? And we say, well, you know what? We're not moving at the extremes, right? We've stopped at both ends, which means we've got no kinetic energy at both spots. So 0 and 0. And at some point, we must have a maximum value. That should happen right in the middle. So this will look kind of like that. And the potential energy one will look kind of like the opposite, because since there's no friction, there's no way for us to lose energy. If there was friction, we have to worry about non-conservative stuff in here. But because there isn't, we're not losing any energy. So we don't have to worry about this changing at all. If we did, then you'd see this slowly kind of, let's do the potential. So slowly down, up, less high, slowly down, and it would damp out and stuff like that. But we're never going to see a question like that because I shouldn't say we'll never see a question like that. Every single question I've seen that has us do simple harmonic motion is on a frictionless surface. Why is the graph parabolic? Okay, so if we look at, we know in this case, the total energy must be a constant. We're not going to gain or lose any energy in here because we have no friction going on, which means this is spring potential plus kinetic must equal a constant. And the potential energy in a spring depends on x squared, which means that this has to be a curve. Because if it was linear, it would depend on x to the first power, not x squared in that graph. Okay, and that's why we have this curve shape and this curve shape going on because of the squared term in our potential energy equation. If we had this depend on something else, how's the Hooke's law playing role in this? So Hooke's law is where we get this from. We know the force on a spring is K times X, and it looks like this for the force and the X value. This means that the work done must be the area of that graph, which since it's a triangle, 1/2 base times height, that's 1/2 kx times x, or 1/2 kx squared. This is where our potential energy in the spring equation actually comes from. The other part Hooke's law could come into play with this is to say, okay, what's the force on the spring when we reach an equilibrium point, or when we've got this tension pulling on it, or something like that. But so Hooke's law gives us the equation for energy in a spring, which lets us figure out the shape of these graphs and stuff like that. But this is also given to you on your reference tables for potential energy in a spring. The other place we might see Hooke's law is if we suddenly flip this to be a vertical problem. And you can say, okay, what's the force on the spring when we're at equilibrium? How far does this stretch? Then you do something like Fs equals mg, because they must be equal to each other. K times x equals mg, x equals mg over k, and something like that if we get a question that talks about a vertically hanging spring. But typically, a lot of these are horizontal in there. The other part that's not energy and graphing is the period of this. And this is probably the other part, square root of m over k, that tells us how long does it take for one of these actions to happen. So for the spring to go from here over back to there, that's a period. That's the time for one complete cycle. And that's where we get this sort of equation coming in. Typically, when I've seen these applied, they're going to do something like, okay, do some energy stuff in here, and then tell me how long does it take to go halfway, or how long does it take to go a quarter of the way through a cycle. So you take this, m's the mass of the spring, k is the spring constant on this, or mass on the spring, and k is the spring constant of the spring, and basically you get to calculate that time. There's also times for vertical springs, horizontal. Yeah, pretty much. Yeah, so going through John, yes, that's exactly what I would do there. Typically, yeah, and they would use an A instead of a X for that, A for amplitude of the motion generally, but yes, that's exactly how you would do it. The only difference would be you'd also have to have potential energy included in there due to gravity. So like if you were to do you do the lowest part. So the most extreme part distance there, that 1/2 mv squared equals 1/2 kx squared would apply. At the highest point, you'd have to worry about gravity in there too, and that gets more complicated. Does mass affect the period? Well, it does for the spring because it's got an m term in it. For a pendulum, we've got TP 2 pi square root of L over G. There is no mass term in there for a pendulum, which means no. For a pendulum, we don't care about what's hanging on the end. For a spring, we do. So one of the questions that will commonly come up is comparing the two. You take a pendulum and a spring and you synchronize them on Earth, then you go to the moon, and then you go from there. And then how are they different? Displacement for these really doesn't make a difference, except for, and I'm sure your teacher mentioned this when they went through stuff, this needs a small angle displacement. So if I'm moving this pendulum up a little bit and letting it swing, and then moving it a little bit more, that will make a big difference. But if I'm making this like a 90-degree pendulum and having it swing down, that is a huge difference. This equation isn't valid anymore. SHM is not uniformly accelerated, correct. Yeah, 15 degrees or less makes that approximation work. So as long as it's small, it'll work. So Hammond, yes, SHM is not uniformly accelerated. We've got an acceleration graph for this that kind of looks like almost a cosine curve, where at the extremes, you have maximum acceleration going on, and at the equilibrium point, you have zero acceleration going on. So it almost looks like a cosine curve going on there for the acceleration. Same deal with velocity and speed. They will look more like sine curves in there, just based on where you're going to see the maximum motion or minimum motion going on there. Okay. But yeah, that essentially is simple harmonic motion. A lot of it deals with energy. So if you can do potential turns into kinetic, turns into potential, and get that sort of graph, that sort of setup going on there, and then apply the correct period equation for the other stuffs in there. A lot of times free response questions for this are going to be an energy question, or maybe a forces question if you're dealing with tensions and stuff like that. And then at the very last part of these, they'll throw on how long does it take for this to happen? Go do stuff on there. So these are really almost added in as an afterthought to an energy or a force question, just to make it hit a simple harmonic motion topic on there. All right. Other questions on SHM? We have to manipulate the actual cosine equations. That's a good question. I don't think so. I think that's an APC topic, but let me look real quick here at the reference tables and see what they give you in terms of that setup. If they give you the equation, which I'm not sure they do, but let's just look it up. on here. No, I don't care about a YouTube video. I don't care. I just want the picture. Show me the reference table. Give me a picture of a reference table. You know, you'd think I'd keep this handy. So they do have the x equals a cos omega, 2 pi ft. Yeah, sorry. 2 pi ft equation on there, which means that they're going to expect you to know that this is actually a cosine curve of some kind, talking about where the mass is on there. Other than that, as far as adding phase shifts in, they don't add a phi term in there, which means we don't have to worry about phase shifts. So, hi, Julie. We are going over simple harmonic motion and any questions and stuff like that with it. So you'll need to know that, for example, if they give you a x versus t graph, it's going to look like a cosine curve where this is your equilibrium position at 0. The time it takes for one cycle lets you figure out the frequency or the period. The height of this is your amplitude, stuff like that. But you're not going to have to worry about, oh, how many degrees is this shifted from this cosine graph, et cetera, et cetera, et cetera. That's not one that you're going to have to deal with entirely. Would the restoring force be positive or negative? Totally depends on where we are. So let me grab some more scrap here. If we had a vertical spring, so let's say we had a spring and a box on here. All right, so you've got gravity pulling down, and let's say our equilibrium line is right here. So we are above our equilibrium position. Fundamental harmonics, frequencies, nodes, antinodes. That is not covered on this year's AP exam, but definitely we can hit that with nodes, antinodes, stuff like that on there. But the waves part of that is not included on this year's AP. So I will hit that in a bit. Okay, so back to this one, vertical spring. Let's say, so we have, so equilibrium position, which means we also have the force of the spring pushing down on it. So if we're calling down positive, then these are both positive things going on. Once we pass through this equilibrium position, so let's pretend we've gone further down here, we still have gravity going down, but now our spring force is pushing up. That would be in the opposite direction. So it kind of depends on which one you define here. If I define at the beginning, it's all positive, then once we're past that equilibrium, we're pulling up on it again, that's got to be a negative force going on there. So it really depends. The force is going to oscillate. Hence, we're getting the sine cosine curve sort of stuff between positive, negative on that. And that really depends what you're calling positive or negative. Will determine when it's positive and when it's negative. But in general, yes, there is definitely there's a time where it's positive and there's a time where it's negative on there. Exactly. Yeah. So whenever you choose this, and this would be the point where your force on the spring would equal 0, hence equilibrium, we are doing, that's where you're going to see your shift in there. Yeah, the restoring force is always to get back to equilibrium, hence the name restoring force on there, and it will always change depending on what it's doing, or change its sign in there. All right, I know there was a lot of more comments in the chat there that I missed. So let's see, we did pendulums, we did that sort of stuff. Waves, antennas, stuff like that. Can we do a total kinetic energy of a system sort of thing? Okay. Sure. Think of a good example here that's not just potential turning into kinetic. Actually, that's going to be simple enough for what we're doing. So scrap over there. Let's say, talking about energy again, and then I'm going to scroll back through what our next topic is here. We got some torque stuff, which we may have to push off till next time. We did conservative, gravity, Kepler's laws of motion. Okay. So let's do a potential kinetic energy sort of thing here. So let's do simple stuff here. We have a ball. with mass m. It's a height h above the ground. We're going to ignore any sort of air friction or any sort of friction in general, and we're asked to find, okay, what's the kinetic energy when it reaches the ground? Okay, this is probably the simplest way we can do it. There'll be more complicated examples, but in general, this is pretty good conservation of energy sort of stuff. All right, so first off, let me preface this by saying there are many different ways of doing this question. Okay, for example, we can use kinematics. You can do something like v squared equals v naught squared plus 2a delta x, and then kinetic energy is 1/2 mv squared. And that would solve it perfectly fine and get us the same exact answer we're going to get eventually. Or you could do it with energy, which will say we started with potential energy due to gravity, and that's all going to turn into kinetic energy. So all the energy we started with goes into kinetic energy because there's no friction. There's no non-conservative forces here, and we're going to define our system to include everything in that picture. We're pretty good. We can just say potential turns into kinetic. So mgh equals 1/2 mv. Actually, we're just looking for kinetic equals kinetic, and we're done. Just potential turns into kinetic. Again, now if this was a moving ball, let's say it was thrown with a speed v, we're doing projectile motion, and we want to find total kinetic energy. Okay, we do the same basic thing. We would say we had potential energy and kinetic energy at the beginning. So we'll put some knots in there and then that will all turn into kinetic energy when we arc through the air and hit the ground. So again, we're going to have mgh, energy from falling this height h, plus the 1/2 mv naught squared term that we started with must equal our kinetic energy at the end. And then depending on the question, we will go through and do the rest from there. But there's a couple basic examples of friction and stuff like that. Wow, we got a ton more questions coming in. Okay, K is kinetic energy in here. Mechanical energy, I always write down as E total, which will be potential plus kinetic. But K, right off your reference tables, K is for kinetic energy in there. Okay. Any other questions on that? We got about 10 minutes left, and there were a lot of questions on torque and rotational and stuff like that. So if we're okay with energy, I'd love to jump over there and hit that up for a little bit before we go any further. Okay. All right, so let's talk about rotation stuff first here. So one of the questions was about torques and lever arm and stuff like that going on. And then another one was about why do we need to have friction in order to roll without skidding? And those two are actually really closely related to each other, which is awesome. So let's start with torques first. So torque, your reference tables define it as a force times a radius that is perpendicular to each other. So for example, if I want to make this pen rotate, I need to push perpendicular to the pen. It doesn't do me any good, hold it this way, to try to make it rotate by pushing on the end. Pushing parallel to the pen doesn't work. Pushing perpendicular does. Okay, which is why this is often written as FR sine theta, where theta is the angle between my pushing and the arm itself. So as long as we have something that is perpendicular, we will get a rotation. We will get a torque going on. If we don't have a rotation or have a perpendicular part, let's say pushing at the end, we won't rotate. Or if we don't have a radius going on here. So radius, the distance away that I'm pushing. So if I'm trying to push on this on the pivot point, 0 radius away, it doesn't matter that I'm pushing perpendicular. We're not going anywhere. Instead, I got to push some distance away, some radius r, and have some part of this motion be perpendicular in order to make this thing actually rotate. All right, so that is torques and lever arm. Lever arm is a big fancy word that means how far away from the pivot are you actually pushing? If we are pushing far enough away, we are going to actually have a torque and maybe be able to rotate because all the torques added together lets us rotate around. So if the radius increases, yeah, that's exactly it. So the radius increases, the torque increases. A great example from childhood and stuff like that would be like on a teeter-totter or a seesaw, and you'd have two different people and you're trying to balance them out. And if you want to balance it out with 3 kids and 1 kid, that 1 kid needs to be farther away from the pivot to make it work. So for example, if I have a big mass M here, I can balance that with a little mass, little m, but it needs to be much further on, okay? So one radius needs to be much bigger than the other radius in order to balance that out, okay? Now, getting back to rolling, friction, slipping, stuff like that. So let's pretend we had a ball. And this happens pretty commonly here. We've got a ball that we want to roll. Key idea here is rolling, not just sliding. Okay. Most of the time this is done on a ramp, but for the ease of it, I'm going to do it right here. This ball will roll because we have a torque. Torque is going to make this rotate. Angular rotation, angular acceleration, start to spin. This happens because there must be something causing it to roll. Okay. Now, if we look at the forces on this thing, we've got gravity going straight down, and we've got, that's what's marking up, friction, I'm going to say for the sake of going backwards. Okay. It doesn't really matter which direction, forwards or backwards. It's going to put front spin or back spin on it. Okay. Now, because of this, we also have normal force, which I probably need a third color for because we're doing this. There we go. Normal force going on. Okay. So because we're looking at our torque definition, a torque must be a force times a radius that is perpendicular to each other. On here, gravity cannot cause this ball to start rolling. It doesn't work. Gravity is perfectly parallel with the radius of this circle. So mg doesn't make a torque. Likewise, the normal force doesn't make a torque because it again is perfectly parallel to the radius of that circle. Cannot make a torque, cannot make it rotate. The only force that we have here that can is friction, because friction makes a very nice perpendicular relationship with that radius. So the torque in this case is the force of friction times the radius of my circle. And this is what's going to cause that thing to rotate. Friction parallel to the surface on the incline. Yeah, as long as we have friction. If you're on a ramp, the same thing applies here. You've got friction pulling up the ramp. There's your radius of the ball. They are perpendicular to each other. That is what's going to cause the ball to roll. If there was no friction, we'd have it just slide down the ramp, just like we did with a box when we studied energy. There was no difference there. So if you have friction, you get to roll. You don't get to slide. And that's also why, if we go back to energy for a second, no friction on this ramp, we can say potential equals kinetic, no big deal here, right? And we get 100% energy transfer on there. With friction, we get potential energy turned into translational and rotational kinetic energy. And that big term is why our velocity at the bottom will be different than our velocity when there was no friction. However much work friction did, it turned potential energy into this rotational energy in there. Yeah, all right. Can an object ever overcome the force of friction and enter a frictionless state? I guess no. When you talk about overcoming the force of friction, just to get it started, you overcome static friction, but you still have kinetic friction going on as you slide through. That's why if you take anything and slide it, you got to push it to start it moving, but eventually it'll come to a stop. So you can overcome static friction, but not kinetic friction. basically we can get that close in a frictionless state if you put enough oil or enough lubrication or other stuff like that, or just say, hey, I'm making this magical physics world that has no friction. That's the only time we can actually get to frictionless, where this ball will just slide perfectly down there, in there. Yeah, we'll always have kinetic friction going on. So you can overcome static, but kinetic kind of lives there. All right. So I will say for you guys, but a ball will always have static. Yes, it will always be static friction with that, because that point of the ball is never actually sliding along. It's always rolling, which is always static friction on there. I don't think that's a tidbit we'll ever have to do it. Yeah, I would always do static friction on there. Or in all of these cases I've ever seen for AP1, you can make it a generic force of friction. And I've never seen them give a question so far where they have to have you differentiate between kinetic friction and static friction on a rotating object sort of question. It's always just been, here's friction, here's a mu, go for it. Or compare with friction or without friction. But yeah, it would be static regardless in this case, unless they talk about it rolling and slipping. If it's slipping, then we have different rules where this doesn't apply. Basically, that's like your tires on a car when you're going too fast. They're still moving, but they don't get enough grip, so we're losing energy in that process. It's not a perfect potential to kinetic sort of thing. It'll be potential to kinetic plus work. What does slipping mean in terms of torque? Basically means the torque for that instance is zero. That force that was working through it, that was going to make this thing rotate, suddenly disappeared, and you would just have it keep going on there. Okay. So yeah, that's 2 o'clock. If you guys want to jot down more things you want to see next week, Wednesday, same time, same place, I'll make a list and make sure we're prepped for those things. I know I didn't get to gravity and Kepler's laws of motion, which I will definitely hit next week. There are apparent weightlessness, so elevator problems. Yep, we'll hit those as well. So we need weightless, elevator, and we need Kepler's. Okay. Does the object keep slipping because of its moment of inertia? It's a tough. Let me think. Does it keep slipping because of its moment of inertia? Yeah. So Juliana, we are planning on doing Q&As physics every Wednesday, basically from here until the exam, I think. First unit of kinematics. Yeah, I can do some projectile motion stuff again. Let's add that to the list. Hey, and also, if you guys are interested, cram passes are coming up pretty soon. I think we're starting those next week, where we're going to go unit by unit, in-depth review and stuff like that for it too. But if you want to stick with the free stuff, definitely we'll hit that as well. Rotation, yeah, so we'll do some more rotation. Okay, yep. So those look like 4 good ones to do for that. So I will hit all those things next Wednesday. 1 o'clock to 2 o'clock, same time, same place. Yeah. All right, cool. Thank you, guys. And I'm going to shut this down. So I will see you all next week on there. All right, have a great day.